A very good morning, all the participants, and we welcome you back, sir, Dr. Nilanjan, sir. I'm very thankful to you, sir, for taking time from your busy schedule and joining us with our FDP. Sir, over to you. Kindly start the session, sir.
Thank you, Dr. Ram. So, a very good morning to all of you. Just 2 minutes. I'm downloading my PPT.
Okay, yes, sir. Sure, sir.
Yeah. Okay.
It is sharing, sir, not showing.
Is it fine now?
No, sir. It is not visible now.
Still not. Okay. So, let me
It will take
share.
1 minute.
Just.
Yes, sir. Now it is visible.
Okay.
Thank
So,
you.
very good morning to all of you. So, today I am going to talk about computer-aided diagnosis. So, what happened when diagnosis is automated? So, from deep learning point of view, I will try to talk or try to give a little bit insight on that. So, worldwide, if you take the statistics, you will see around say 400 million people they don't have health services. They not actually get the health services, and almost 100 million people they push towards below poverty line because of the health expenses. So that actually tells that what is the current scenario. And the second thing is in India, doctor, how much time used to spend per patient. That is also interesting. In India, a doctor used to spend 2 to 2.3 minutes on an average time. The number in English is 48 seconds. So 48 seconds, a doctor used to, diagnose our patient. So now imagine actually it's 21 minutes. If the number is 2 minutes, there is a high chance that there will be a problem of error. The error can be there. So medical error started again. Okay. I think now I'm audible clearly.
Yes,
Hello.
sir. Yes, sir.
Some people are saying that voice is cracking. Okay, so that means in India only 2 minutes doctors used to spend on an average per patient. So there is a high chance that human biasness will come into the picture. So that's why the chances of error getting higher, the biasness is getting higher. So as an engineer, we need to design or develop some software which actually helps the doctor for, better assessment, faster assessment, and revalidate whatever they are diagnosing, need to revalidate. So for cross validation, we need to come up with some software. Now, regarding the CAD, before going to the CAD, what is CAD? CAD actually are complex systems, which is actually human driven. You can say from the qualitative framework to a quantitative framework, it's a transformation. It's a paradigm shift. So from qualitative knowledge, the doctors are having the qualitative knowledge. So from there, by using, say, radiological assessment, by using image processing or machine learning, etc., through some CAD system, we come up with some quantitative framework. So it always gives a second opinion to the radiologist. It always helps the radiologist to come up with a faster decision. And apart from the rapid decision, the decision needs to be accurate, consistent, and it always helps the radiologist to cross-validate. So whatever they are diagnosing, that need to be cross-validated by a CAD system. So CAD system is basically works as a helping hand for the doctors. So again, I am repeating, from the qualitative paradigm, it actually helps to change to quantitative paradigm by means of image analysis, radiological image assessment, or say deploying of AI or say ML, etc., through some CAD system. So it's a paradigm shift. And this shipment always actually helps the radiologist to come up with a rapid, accurate, and consistent decision. So that is the main motivation of designing CAD system or computer-aided diagnosis system. Now, typically, there are three different categories of CAD. The first category is called the computer-aided detection, CAD-E category. Second category is called the computer-aided diagnosis, which is CAD-X category. And the third one, computer-aided diagnosis quantification, which is called the CAD-Q category. So the first category, that is the CAD-E category, tells you the location of potential disease. It may be cancer. So it tried to find out the location of potential one particular disease. Second is the CADX. CADX will tell you the likelihood that that particular lesion, it is a benign or it's a malignant. So it always tells you the likelihood. So the first one, CAD-E, tells you the location of the potential particular disease. Second tells you the likelihood of that particular disease, typecasting. And the last one, that is the quantitative measure. So quantity basically tells you that if you have a tumor or if you have a lesion, and it try to quantify. So there are three different categories of software. One is CAD-E, that is the computer-aided detection. One is CAD-X, that is computer-aided diagnosis. And the last one is computer-aided quantification, which actually helps to quantify a particular type of disease. So these all three different types of software are clubbed together and it comes under a particular umbrella. That umbrella is called CAD, which is Clinical Decision Support System. So now, if you go through the different image modalities, medical image modalities, say starting from CT, mammogram, MR, ultrasound, radiological images, say ophthalmo images, derma images, endoscopy, etc., you will see majority of the image modality, almost 75%, they are actually covers radiological images. Under radiological images, the CT, mammogram, say MR images or ultrasound images or radiological images will come. So these covers the radiological images. So CAD system basically we used to deploy on radiological images. But apart from radiological images, if it is microscopic image, if it is a retinographic image or say derma image or say endoscopy image, then also we can deploy CAD system. But if you check all different types of modality, you will see almost or on an average 75% of image modality actually comes from the radiological images. But it not necessarily, it means that the CAD system only works on radiological images. Not only that, it might work derma images, it might work for the ophthalmo images, it might work for the endoscopic or other different modalities also. But the number of work is very less. The number of more in particularly in radiological images. Now then comes, so diagnostic images, if you study, you will see the radiological images covers the ultrasound, MR, your CT images, your X-ray, 2D radiological images, say if PET is also comes under that. So these are all radiological images where in general we used to deploy the CAD system. But apart from these, the visible light, say photography, like say derma images or endoscopy, or say printed say signals or the waves, EEG, EOG, ECG, PPG, PCG, etc. or say microscopic images like say light microscope or say electronic microscope, transmission microscopic images, etc. or 3D reconstruction. These are different diagnostic images. So majority of the work carried out in particularly radiological imaging. So to me, CAD system is nothing but a complex pattern recognition problem. So if you can have an X-ray, in that X-ray, if there is some suspicious structure, what you need to first dump thousands of data. Once you put thousands of data, then you try to come up with some optimized algorithm, which will be very much rational, which will be very much generic for any kind of patient data. So irrespective of the demographics, irrespective of the ethnicity, irrespective of a particular disease or a symptom, the data, the algorithm should work in general in a normalized fashion, in a generic for all types of different types of data set. So that's why we need to store all the medical data into a CAD server. CAD server in generally store diagram format data. Diagram format data is a very high quality data. But apart from that data might be, there are some data, maybe QTB format data. So the QTB format data, which is very easily available data. QTB format data are very noisy data, perturbated data, low quality data. So if you are lucky, you have diagram images. But if you are not lucky, you will get different images, which are almost, the full of noisy image and perturbated images. And that is the major challenge of medical imaging. The image are mostly dark image, blur image, and they are not that much enhanced, perturbated image, noisy image. But if you have diagram image, you are lucky because you have lots of, it carries actually lots of storage space and the quality of the image is very good. So you need not to go for any kind of pre-processing kind of stuffs. So once you have non-diagram image, then you need to go for some certain techniques which actually enhance the quality of the image. So those demands the pre-processing. So initially, if we think about from the shallow machine learning point of view, not from the deep machine learning view, from purview. So the basic step is the pre-processing, because as I said, most of the radiological images, they are perturbated image, they are noisy image, they are dark image, they are not quality enhanced image, the brightness level is poor, the contrast levels is poor. So you need to enhance the quality. So first thing is you have to reduce the artifacts. You have to reduce the noise level. You have to label the image. You have to go for filtering technique. So all these are actually related with the pre-processing. So if you have uneven illumination, that illumination need to be even. If you have brightness, sometimes might be the contrast need to be stretched. Sometimes you need to deploy some certain filter. That filter will remove the noise, etc. So in this way, you can enhance the quality of the image. But remember one thing, once you improve the quality of the image, it should not destroy the diagnostic value of that particular image. If the diagnostic measures of the image is somehow get lost, that means you are losing information. See, pre-processing, once you are doing, you are actually going far away from the actual image. So there is a high chance that you are losing the diagnostic measures. So you have to always try to retain those diagnostic measures. In that way, we can only pre-process. The second thing is you have to segment it. You did not to put the whole image, rather you try to only particularly focus on the region of interest area. Now, region of interest area, once you try to segment it, you have to you have to partition the image into some certain disjoint sets. There will be a foreground, there will be a background, and you try to find out the region of interest. Now, once you're able to find out the region of interest, you're trying to find out the compactness, try to find out the form, shape, size, location, etc. So once you have all localization properties, you have the shape information, you have the form information, location information. Then what you do, you put some certain evaluation, some traditional machine learning framework, and after that it will try to classify and it will give you some result. So it's similar, looks like something like this. If you have a, say, diagram image, if there is a CAD server, you would read the image, go for pre-processing, extract the region of interest, start selecting the features, go for classification, you try to predict, and then you get the diagnostic result. And ultimately, if the results are poor, it will again try to process. Otherwise, the diagnostic results are good, so it can be acceptable. So this was actually long back, say 10 years back in 2010, around 11, 12. That time, once completely it was on self learning framework. We used to do all these things in this way. But it not mean that till date we are all doing only deep learning stuffs. This also works. Yes, there is some basic changes comes into the picture. But on an average, this was the shallow machine learning framework where we change the different pre-processing technique, we change the selection mechanism, we change the classifier, and we get different results, and we are happy with the result. So as I said in my last day talk, that once you get some accuracy, say maybe the model prediction is giving you 90% accuracy or 99% accuracy, there is always a trust issue. And once there is a trust issue, you have to go for some explainable AI, because explainable AI is the only thing which actually explain why you are getting that good result or maybe the bad result. So that explainability of the model was not previously there, which is now we people started thinking in that way, that our explainability of the model should be there. The model should be explainable. Okay, so this was the basic framework. I will try to go one by one, and I will try to tell what are the different challenges. Then I will move slowly into the deep learning framework. So first thing is the image segmentation. Image segmentation is nothing but, as you, already covered 5, 6 days, different sessions. So segmentation is nothing but partitioning the image based on some certain value. Maybe the value can be the gray value, maybe the color, maybe the texture, maybe the brightness, maybe the contrast level. You are trying to split your image. Why? The storage of the image should be lesser, because if you represent the image into 2 gray shade or say 3 gray shade, then automatically the number of variations of the gray will be lesser and the storage space will be lesser. So in this way, you can partition the image into foreground and background. You partition the image into region of interest, non-region of interest. So in this way, we always try to find out that this particular location is my actual interest region. But there are different challenges in medical image segmentation, which are not there in other kind of segmentation. Let's suppose there is a disease called atherosclerosis. What is that disease? That disease is inside the artery group, calcium deposited, and there will be a blood flow from your coronary to your carotid. The blood flow to your brain, that is getting hampered. So what I need to do, I have to put a probe, and the probe will rotate and emit sound wave, and the sound wave will refract from the inner wall of the artery. So inside the artery wall, if there is calcium, the refractive index of the sound, and in the part where there is no calcium, the refractive index of the sound will be different. Based on that, we try to find out how much calcium is amalgamated inside your artery. That was fine. This is called the intravascular ultrasound imaging. Now, what is the problem? The problem is, if you put a probe, the probe actually having a shadow. And once the probe having shadow, that shadow covers some calcium region. So if you try to segment inside the artery wall, you are not be able to segment that part which is under shadow. Think in this way. There is a drone, it captured the number of vehicles. There is a bus. Within that shadow of the bus, there are 2 bicycles. So the drone able to capture the image, aerial image, but it failed to detect 2 cycles because it is within that shadow region of the bus. So until you remove the shadow, you will never be able to find out the exact number of the vehicle. Same thing. You are putting a probe, and the probe having one shadow, and within that shadow region, remove the shadow, you will never be able to find out fast. Second thing is, if you check into any radiological images, you will see the gray value are very close to each other. That means that band is very narrow. So it is always difficult to separate out one from other. Third thing is, if it is full of noise, if you try to segment, then you will see there are presence of artifacts. If the all calcium amalgamated in a single place, it is easy to segment. But if there are small pieces, it is very difficult. This is called the partial volume effect. That means the volume is not actually coagulated in a single place. So if it is not amalgamated in a single place, if it is a multifocal disease, that means it's all the calcium lies a small calcium all around the path of the artery, then it is very difficult to segment because it's not amalgamated in a single place. They are scattered. So partial volume actually affects. So the closeness of the gray value is other different issue. So these type of challenges are there in medical image segmentation, which you actually not face in any other type of image segmentation. Maybe, I may not, but maybe. But these challenges are there. So the very first technique was based on the threshold value. So we try to find out some threshold value. So this one is threshold T1 and T2. So this part will be substitute 0 to 55 by say 50, 55 onwards to 200 represented by 100, and 200 onwards will be represented by say 210. So we are representing these three value into three different segment, three gray value. So there are two T1 and T2. Now the challenge is the selection of T1, T2. So if you change the image modality, if you change the patient, if you change the patient alignment based on anything, the T1, T2 value can change. So you can't set these T1, T2 or the threshold value manually. You can do it automated way, which is called the adaptive technique, but adaptive technique is also sometimes not gives you optimal result. So in such type of cases, there is a huge scope of working by deploying meta-heuristic and heuristic algorithm to find out the optimal T1, T2 value. For any kind of images, radiological images, if you try to find out the T1, T2 value by using some heuristic or meta-heuristic algorithm like say PSO, GA, and colony optimization, or say search, but say BAT algorithm, there are tsunami of meta-heuristic algorithm. So you can deploy any kind of machine learning algorithm just to find out this T1 and T2. And these T1 and T2 will be different for all different modalities. It is not common for any particular type of image. It's not always it will be same for the MR images. It's not like that. Or CT images, it's not like that. Even for the patient also, if you change the patient, this T1, T2 will be different. And these optimized value will be determined by the heuristic algorithm. So this is one area where some people can work. Look into these two images. These two images are apparently looks to you completely different image. But believe me, as an image processing guy, you have to believe that these the appearance is different, but if you study the histogram, you will see the RGB histogram is similar. Professor Pass and then group 1997, they reported these particular two images where these particular two images histogram is exactly same. Think about it, how difficult it is if you go for threshold based technique based on the histogram. So these are the different challenges or the limitations threshold based technique. The second technique is called the age based technique, which is called the contour based segmentation. You try to capture the contour, maybe with a Canny, Sobel, Pivot, or Robert, etc. So you try to find the ages. Now think about it. If the age is full of noise, so whatever you are detecting the ages is not actually age. They are but noise. So you are detected false ages. So detection of false ages will give you wrong segmentation result. So you need to somehow have to ensure that whatever the age you are trying to segment, that ages are correct ages, not the false ages. So if the noise is there, if the noise present in that image, then there is a high chance if you go for age-based segmentation, if you try to split it, there is a high chance that there will be full of noise. So what to do? The thing is, you can remove the noise. How can you remove the noise? You can remove by using some filter. Now, that filter should not actually spoil the essence of age. Means the dy dx information should retain. So how can you do this? You have to use some sort of filtering technique where the age information should be preserved. Means we have to use some kind of filter where the filter will start working and it will work everywhere except the ages. So once there is an age, that means there is a dy dx change. It's not informed. There is a dy dx changing. The filter will stop working and the age information will preserve. Then after that, the filter will work. So in this way, we can preserve the age information by age preserving filter. And in this way, the false age detection can be resolved and the age-based segmentation may give you better result. So in such kind of CT imaging, you will see there are lots of studies carried out where we go for image-based segmentation. So age preserving filtering designing is another research challenge where you can work, where you can come up with different filtering technique where the age information can be preserved, which actually helps to retain the diagnostic values of the image. The last category is called the region-based segmentation. So region-based segmentation is you are having this image, you are trying to find out some seed point, then you grow those seed point based on the gray value, and also these values are say compacted, then it will give you one big chunk of say pixels. So this is called the region growing. Or other way you can do by region splitting. So based on the gray value, you split this. There is a high chance that it will go for under segmentation or over segmentation because you are trying to merge or you are trying to split. So the optimal number of segmented part selection is another challenging task. You have to select where I should stop so that this will not go under segmentation or over segmentation. So if you're working with say brain image and if you're going for over segmentation, if you start medication, it might happen, it will go for paralysis. The patient will go for paralysis. So such type of cases is not desirable. So what we need to do, we have to somehow avoid the under segmentation or over segmentation cases by simply choosing some optimization technique where this optimization technique will actually select the number of segmented parts. In this way, we can actually go for enhancing the quality of the region-based segmentation. So these are the typical three categories of segmentation which we deploy any kind of CAD system. One is called the threshold based, one is called the age based, and last one is called the region based segmentation. So all these three techniques have their own limitation. So what we do, we try to merge infuse the region based or age based, or say age based with the say threshold based, and we try to come up with some hybrid technique. And many of the cases image modality will see that hybrid technique gives better results. And I mean, it is always good to test different algorithm, combination of different algorithm. So under region based, there are n number of algorithms. Under age based, there are m number of algorithms. Under threshold based, there are say k number of algorithms. So you can come up with n into k into m, that combination, any kind of hybrid technique. So those technique might gives you some type sort of better result, this combined result. Then after that it comes, see this is an example, like this is an active control model, this is your input image, and there is initially we are trying to iterate. You are trying to fit a polynomial curve. That polymetric, what this polymetric curve, what it is doing, it is trying after some certain iteration, it is trying to freeze that curve in such a way that the energy should be minimum. And this is given by KEC and their group in 87. It's a long back algorithm, which is called the ACM or active contour model. And there are lots of variants of this particular model, like snake model and blah, 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 where we try to do based on the contour information, we try to fit in a curve. That volumetric curve will fit in such a way that the energy should be maximum and it will stop working. So now the question is it region, say, splitting merging, or is it contour based algorithm? So this is an open question. So is it an contour based segmentation, or it's a region based segmentation, or it is a combined, means it's a hybrid one? So you explore these things. That contour based segmentation or this active contour model is basically what type of segmentation? Is it global region based or something like this? Okay, so in this so different I mean the algorithms are infused, and people started deploying into different modality, and different say machine learning frameworks gives various results, and ultimately the work published. This was the I mean long back we tried to do in this way, but now the things are different. It's not only that segmentation, we are actually trying to avoid the segmentation, because all these segmentations have their own limitations. Now once you have this segmented value, then the second thing is you have to compare, and you have to tell that the whatever the result you obtained, that result, segmented result, is good. So for that you have to benchmark. You have to benchmark with the doctor's hand trace data. So once the doctor will provide you benchmark, maybe say the ground truth is given by the red color, traced one, and the blue color is your outcome, your manual segment, say segmentation by the automated system or the CAD system. Then you try to compare. If the variability is too high, that means you are far away from the doctor's hand trace. If the variability is very low, that means you are close to each other. And this can be determined by a measure which is called figure of merit, or sometimes it is also called precision of merit, which is 100 minus auto minus GT. Auto means the automated one. GT means ground truth divided by GT into 100. And this will tell you, say 90% accurately, we are very close to doctor's hand trace. And if you don't believe a particular doctor, don't rely, you have to trust, you can consider 3 doctors hand trace, and you can take a mean. That you can do. So that will be a average benchmark. So that average benchmark you try to compare, and you represent some figure of merit or precision of merit, and that will give you better result. So this is called the intra-observer, or it might be the intra-observer variability. So within the observer or between the observer, the variability can be checked. So in this way, you can come up with some ground truth. So just 2 minutes. Until now, am I clearly audible? Can you please type in the text box?
Audible.
Okay. So the next part is, so once you have the ground truth, so you properly able to segment a particular, say, region of interest. Now you have to extract the features. So for traditional machine learning, the one of the feature is a prominent feature, which is called the color-based feature. But fortunately, unfortunately, most of the medical image, if you study radiological images, it's not colored. Only the colored images, the ophthalmo images or the derma images, or might be sometimes the teeth images, those are basically some color images. So color image, like if there is a disease called diabetes. In the diabetes, what happens? There are macrocalcification or soft exudate, hard exudate, hemorrhage. All these can be detected by the presence of a patch of yellow color. And this yellow color actually plays a significant role. Some cases where the color plays a significant feature, this plays a role. But radiological images, most of the cases, color feature not works very prominently. But few cases like ophthalmic images, radiological, say, or derma images, this type of color feature works fine. The second one is the texture feature. Like say these mice have say fibrosis we are trying to treat. If fibrosis level 1, level 2, level 3, so the can grow. So here we try to form different patches. These are all toggle patches. So we have toggled it just to show that they are different from each other. They are different from each other. So all are different. So in this way, you can prominently you can identify these are different fibrosis level. So this is level 1, level 2, level 3. So fibrosis can be detected by texture. In the case of breast cancer classification, you will see the presence of fat. Is it a fat or it's a fat granular or it's a dense fat that can be also classified by texture. So this is another area in medical image. The presence of fat can be detected by the texture. Now, think about it. This is an input image, and this particular pixel is 105, and these are the neighborhood pixel. These are the neighborhood pixels. And we convert it into such a way that if it is lesser than 105, I will represent by 0. Otherwise, I will represent by 1. And I will start scanning these values. And this will give me a, say, array. This 1D array is basically the scanned version, 0, 1, 0, 1, 0, 1, 1, 0. Or you can start from here also, 1, 0, 1, 0, 1, 1, 0, 0. Or you can start from here also, 0, 1, 0, 1, 1, 0, 0, 1. So this will give you different value. And from that, this particular binary value you represent here as a LBP image. So here what I'm doing, this particular pixel value actually takes all the neighborhood information and it is converting into this particular pixel value. So in this way, one image can be converted into a LBP image. From that LBP, we come to the histogram, we take the histogram and certain number of bean we consider as a feature, and those feature vector we can use for the training purpose. So this is very old technique, but widely used technique, which is called the local binary pattern, where we actually in ultrasound images, it works very nice. There are lots of variants of local binary pattern, but this is, the easiest one. This is the oldest one, where one particular image, we try to threshold it based on the pixel value, which convert it into a binary string, and that represented into a decimal value, and this value actually carries all the information of the neighborhood pixel, and all the pixels value of this input image is converted into in such a way into LBP image. An LBP image, then you try to histogram, find out the histogram. That histogram collectedly you can bucket it. You can select certain number of say pixel values, histogram bin. Then after that, this feature can be used for the training purpose. And the last category is a safe feature. Safe feature means suppose there is a, say, this ligament is inflamed and this periodontal ligament, and this inflammation you try to train your system. So what you will do, you will try to fit an ellipse. Then from that ellipse, you try to find out the deformation. So the deformation needs to be trained. So you'll try to deform, try to find out the deformation by fitting an elliptical curve. That ellipse actually tells you that how much deformation are there. So in this way, shape-based study also can be done. So these are three prominent features like color feature, texture feature, shape feature. Under these, there are lots of different features. Like say texture feature, there are GLCM feature, heraldic feature, etc., etc. So all are different types of feature comes under these three categories of feature. So this is the one example where texture feature and the color feature plays some important role in melanoma or say your mammography study or maybe the glaucoma, etc. Then comes, so you have segmented outcome, you have features, and you have lots of features. So the number of parameters to learn, feature or etc. The data set is less. So what will be the problem? That's small data problem. Last day I discussed. So first problem is always try to the variance estimation, large variance of estimation there. There is always a chance of overfitting. The training will be increased exponentially as the number of feature increases and as a number of data you want to fit in. That means irrelevant attribute will comes into the picture. So data can be duplicate, data can be poor predictor. So lots of data, lots of attributes is always not good. Actually, it's a kind of dimensional cuts. These cuts need to be rectified. So the solution is you have to rank those features. You have to find out the good features. You have to find out the good inputs. So for this searching procedure, what I have to do, I have to find out a quality of feature or the good set of feature. So for good set of feature, we need to go for some selection mechanism. The selection mechanism can be based on the statistical measures. If it is a continuous features, response is also continuous, feature is also continuous, we will go for Pearson correlation. If it is categorical continuous, we will go for LDA. If it is categorical continuous, we will go for ANOVA. If it is categorical, we will go for the chess square error. So it's all depends on the dependent or independent variable, and you should got what type of testing, the statistical measure. So similar, same thing. So in this way, what you try to do from the entire pool of the features, you are trying to filter out some certain number of features who are redundant, who are not contributing that much. Those need to be selected properly. Other way, you can also wrap up. You count a small set of feature, you increase more and more feature, and you get the training result until the performance improves. You are doing repeat the same process. That is called the wrapping method. There is a third technique which is called the hybrid, which is basically a combination of this filter and wrapping technique. So one is the filtering technique, one is the wrapping technique. Is basically the inverse of each other, and the last one is the collective one, that is the combined one, embedded one, ensemble rather better to say. So in this way, you can find out three different types of hybrid filtering and wrapping method for the selection. So you have a less number of feature, good number of feature. Then what to do? Another technique is, suppose there is a, say, this is one, I'm trying to form a hierarchy tree, less than 5 legs. If it is yes, hide under the bed. If it is say no, is it makes honey? No, mosquito. If it is yes, honeybee. So to find out the honeybee and mosquito, which one is a prominent feature? Makes honey or under the bed or more than 5 legs? The answer is more than 5 legs. So that means always the root node is the strongest feature, not the leaf node, not this one. So always we try to find out the root node. So root node is the most prominent one rather than the intermediate nodes. So in this way, we can actually select the best feature amongst those features, and we can choose only one feature. We can opt one feature, and then in this way, you can go for the selection also. So this is based on the decision tree model, where we try to find out the best feature amongst a couple of other features. So until now, this was very generic thing. Then once you have features, you put it to some classifier, and there are n number of classifier. So K, say starting from say any kind of KNN or CNN or PNN or your random forest, AdaBoost, SBM, whatever. So depending upon your data set, the number of features and the nature of the data, you try to fit it into some different classifier, and the classifier or some prediction model that will give you some classification accuracy or prediction result, and you will be happy with that result. So until this, it was all about shallow machine learning. Where was the problem? The problem was the most significant feature finding. Think from the image segmentation point of view. All types of three types of segmentation process have their lots of limitation. All different types of feature selection mechanism, they have lots of challenges. All different types of reduction mechanism, they have lots of difficulties. So all these things need to be properly clubbed together to get a good result by some classifier. It is in fact a tedious task, because you need to manually extract those features. So people started thinking in a different way, that there should be some mechanism where we will not do the segmentation, selection, etc. Rather, it will be some sort of black box where I will give the input as an image and I will get the accuracy as an output. And this is basically nothing but so-called deep learning, where the local pattern ensemble together to find out a larger pattern, that ensemble together to find out a more larger pattern. So deep learning framework, there is as such nothing new. The new thing is we have to come up with a robust system with a large data, which will give you high accuracy and a rapid processing time, which is very important for any kind of clinical data processing, because time is a big factor for any kind of diagnosing. So that's why people started thinking about CNN CAD system or convolution neural network CAD system. So initially there was image, then segmentation, feature selection, classifier, result, but now it's a kind of image, input image is passed through neural network and you will get some result, and that is the so-called deep learning framework. Okay, so I will try to give a case study so that it will be easier for all of you to understand that how it actually deployed into different other modalities. Okay, just 2 minutes. Again. So until now, we don't have any comments. Yes. So still it is audible and visible.
Yes, sir. Audible. Audible.
Okay. So talking about a particular disease, the disease is called silent tip set. Now, why I'm talking about tip of sight? Why I'm talking about glaucoma? See, why do we do study? You will see there is a very common cause of blindness, and almost 20 million people lost their vision because of one particular disease, which is called cataract. But we not talk about more on cataract. Rather, we talk more on glaucoma. The vision loss number is 20 million people, whereas in glaucoma, the number is 6.7 million people. So almost one. Now, why we talk about glaucoma? Why not we talk about cataract as a researcher? Because cataract is a kind of disease which is basically, it actually cloud the lens, and this replacement of the cloudy lens takes a 15 minutes operation. So that's why it can be curable. But glaucoma is a disease which is almost the second disease of blindness. Glaucoma is not curable. As the glaucoma is not curable, so there is only one solution, that is the early detection, and it needs to slow down the progress of glaucoma. So that's why lots of work has been carried out. People always try to do that, they try to detect the glaucoma as early as possible so that they can slow down the progress of glaucoma. So that is the motivation, which are not curable disease, just to find out as early as possible that you have a glaucoma, and it actually resists the progress of glaucoma. But there is a big problem. The problem is glaucoma having no sign. It's a silent tip of sight. So there is no pain, no symptom, no wonder. It's called a silent tip. So there is no pain, as of there is as such no pain, no symptom ever. You will simply lost. So how doctors can understand that you are losing your vision because of glaucoma? There are three ways. You have to measure the pressure of your eye. You have to measure the thickness of your optical nerve, and you have to study the peripheral vision. Now, if any of them is getting affected, that actually signify that you might have glaucoma. So again, I am repeating, this is very important because there is no pain, no symptom. So no ways at all for you to know that you are having glaucoma. So that's why if you study the nervous system, the optical nerve, you will see the left eye is connected with the right hemisphere and the right eye is connected with the left hemisphere. So the optical nerve actually carries the impulse of sight from retina to the brain. Now millions of retinal nerve fibers are bundled together and exit to the back side of the optic nerve and it passes to the hemisphere. Approximately 1.2 million fibers are there in each optical nerve. Imagine, one optical nerve contains 1.2 million fibers, and all are actually passed through the darkest part of an eye, which is the most sensitive part of an eye, which is called macula. From macula, most of these fibers, as a formation of optical nerve, it goes through, it passes through the back of the eye, the hemisphere, which actually carries the impulse for sight. How it actually works. Now, if you look into the front side, you will see there is an optical cup, there is an optical disc. These measures are called the superior, nasal, inferior, and temporal. And this is called the neuroretinal rim. Now, this is cup and the disc. In between, there is a optical cup to disc ratio. It should not cross 0.58. If it is above 0.58, it's a clear case of glaucoma. So that's why we need to study the cup to disc ratio. Now here, if you study here, you will see as that is the number of this, say, optical cup, the loss or the blood flow of the optical nerve, it will increase the pressure. So once it increases the pressure, the blood pressure, what will happen? The blood flow, or the fiber will begin die. So once the fiber will be less, there is a chance of ophthalmo diseases. So pressure increase inside the eye actually increases the blood flow, and that blood flow ultimately affect the nerve fibers, and that nerve fibers are pass through macula, it pass to the brain, and it carries the impulse. It will hamper the eyesight. Okay, so here optical cup to disc, and you can see this cup to disc here, it is very narrow. Here the rim is much more higher, and this is a very common eye, normal eye. This is getting deformed. Optical cup is getting higher in radii, and here cup and disc ratio, they almost touch each other. That means it's an acute case of glaucoma. Now, here this cup to glaucoma, this disc ratio, you will see this damage, and this is the disability, and ultimately lost their vision. So how these measures are there? Actually, this is called 6/10, but the correct measure is 0.58 as per my knowledge concern. So this is how glaucoma progress you can resist. So now think from the image processing point of view. This is r theta, this is r, this is theta, and this is in your Cartesian coordinate. We are plotting this optical cup and this. And if you put into r theta Cartesian, then what will happen from Cartesian to polar? It will look like something like this. And if the polar, it will be easier to process. You can project and you can select this part. You can also project and you can select the second layer, and you can easily detect the cup to disc. And then from polar, you again convert to Cartesian, and it will give you circle, and you detect it. You can properly segment it. So the segmentation is very important because you have to find out the radii. So that's why polar to Cartesian conversion from Cartesian to polar is required to find out the correct measure. there is a old technique which is called 88 technique, which is called ISNT technique. What is ISNT technique? ISNT technique is basically this measures that is the inferior is higher than the superior, superior is higher than the nasal, nasal is higher than the temporal. Plus, 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 and plus, 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 plus. So always this one is the highest one, that is the inferior. This one is the superior. This is the nasal, and the last one is the temporal. These measures are correct measures. These measures are common for all good eye. If this measure changes, if the inferior getting lesser than the superior, there is a problem. So that needs to be identified properly. So inferior, superior, nasal, and temporal, you need to study. It's not always the correct one. That I mean, all same. It's not same value. They are different. Optical cup to disc. If you study, so we are taking the projected view. This is the projected portfolio. Say one side, and this is another size X and Y both sides. Now comes to this one. So in this way, by projection, by Cartesian or polar, by using different segmentation technique, by filtering technique, ultimately you can extract the optical disc pixel from where you will start measuring the optical cup to disc. You can find out the boundary by doing boundary approximation algorithms, gradient algorithm, and you can find out this is optical cup, or you can also this with optical cup and the disc. So these are different segmentation result. Maybe the fuzzy Siemens or say CHT, or the ground truth is also given in green color. So you can find out that how good your accuracy or how good your precision is to find out the actual result. Then the optical cup find there are also a number of segmentation you deploy. So you can find out the cup and disc both by segmentation. And this is the NP here, true positive, false negative, etc. From there you can find out some F measures by which you can say how good your optical cup to disc detection is, and in this way you can find out the chances of glaucoma also. This is a manual segmented one. This is called the OCT image. There's an optical tomographic image, and ultimately once you have some segmented result, it might happen that whenever you are detecting some circle by some automated system which is not giving a good result, so you need to manually tune this. Maybe out of 100 cases, 3 cases where because of the brightness the result is not correct, so doctors can hand trace, doctor can manually tune it, and this is called post processing, which is basically one type of semi automated system where we used to provide the doctors an interface by which those data it needs to be properly tuned by the doctors by using human experience and expertise. In this way, we can also reduce the false positive cases. So this is semi-automated system. These are the tuners. So by tuning those, the doctors can come up and come with a good result, and that will actually improve the accuracy, further accuracy. So it's a kind of post-processing as we used to do pre-processing. Similarly, post-processing also can be done for the semi-automated system. So glaucoma diagnosis, the support system. So we extract the features, we find out the subset of the features, come up with some decision rules, and ultimately also another way we can see this is the different images, modalities, acquisition system, picture extraction. So this is all about the shallow machine learning and pattern classification. You are getting the training results, and ultimately from there optical cup to disc ratio, is this glaucoma or normal, you ultimately find out that you have glaucoma or not glaucoma. So it's a kind of semi-automated system using pattern recognition. So last one from out this particular disease, the output feature generation. You can go for different channel extraction, equalizing the channel, group the features, and get the output features. So ultimately, this I was trying to map with the shallow machine learning with the actual one and the case. But now we switch from CNN CAT system for this particular disease also, the glaucoma also. And here we are actually switching from that particular era to another era systematic. till now anyone having, if any having question, please type. Now comes to the learning. What is learning? The word learning means we are trying to automate search process for better representation. So you always try to come up with a better representation of our data, analyze any kind of study, and that is called the learning. So the main objective of learning is the way of representation need to be tuned in such a way that the data can be useful for the analyzation purpose. So think about it. There is a Cartesian coordinate. There are two different geometric shapes, circle and the rectangle, and we are trying to put a separator like a kernel that will actually separate these two geometric shapes from each other. So how can you draw a straight line which will, I mean, not only straight line, rather how can you partition these two data, separate those two data by using a kernel? Apparently, it looks to you that if I draw a straight line, it is not possible to separate these two geometric shapes. Now think in a different way, think in a learning different way, better representation of this, and think in this way, we are representing the Cartesian data into a polar form. How it will look like? The polar representation will be something like this, r theta representation. Now it will be easier for you to draw a straight line and you can separate these two data. Then once you have this, then after that from polar you can again back to the Cartesian, and that will be a circle. So in fact, it is not possible to draw a straight line in this particular data set. But if you represent the data into a better form, better way, might be that problem can be resolved. So that is the basic essence of deep learning. So Professor Goodfellow, 2016, he first proposed these things, and he's shown that the different kinds of neural network, once we talk about the, see, deep learning is nothing but the representation learning using a kind of different neural network where you try to optimize the hyperplane in such a way that the data should be represented, might not be solvable in one particular typecasting, but if you change the hyperplane, if you optimize the hyperplane, might be that problem can be resolvable, and that better representation is carried out by deep learning. So again, deep learning is a learning system which is almost similar with neural network. There is no such difference. The different kinds of neural where in such way the data representation should be used. That is the main objective of deep learning. Now, before going to this CNN and all, let's try to see some mathematics. Suppose this is my matrix. This is one matrix. In this matrix, I try to find out 4, the number 4. And this matrix I want to use for the training purpose, neural training purpose. Now, neural network doesn't understand this as a whole matrix. What you need to do, you have to flatten it into a 1D matrix, basically an array. And this array will be the input matrix of the neural network, this one. So this image need to be flattened and it will be a 1D kind of vector, and there will be different values. And I have to find out 4 is present there or not. That is my objective. So first thing is, somehow I have to change or flatten the 2D image into 1D image. And we have to then find out the value 4. Now here, finding the 4 in huge, say, vector is always a tedious job, and sometimes it's almost impossible for human to identify where the 4 is. So what I need to do, I need to intensify value of 4 from 4 to say 400. So if you intensify the value from 4 to 400, that will be easily identifiable for human being. Think from machine point of view also. If you somehow amplify the value of individual pixel, that amplification will ultimately improve the identification of the machine. So that's why what we will do, we will not try to find out 4, rather we will try to multiply some weight with all those values, so that all those value will be intensified and the differences between two value will also increase. Like if there was 3 and 4, the difference is 1. But if you multiply with 3, 3 into 3 will be 9, 3 into 4 will be 12. So the difference will also increase by 3. That means increasing of differences will actually helps to identify two distinguished number. In this way, which actually possible, where we try to always amplify the number or intensify the number by multiplying on weight. That weight is basically, here we pass into the neural network, and that amplifies those value to separate out values from each other to prominently make it visible so that the machine can recognize. So that's why weight multiplication is important. Now, second thing is, once you try to multiply the weight, the main challenge is once you convert from 2D to 1D, the spatial information getting hampered. You not be able to identify this is XY. You don't know from where this 4 value is coming because you lost that spatial information. So we have to keep in mind that we have to do something so that the value will be intensified, but we will not, what we will not do, we will not change it into 1D. So we need to keep the matrix as it is, and that is our objective. The matrix will go as a whole. The matrix will go as a whole into the system, not 1D matrix. So what we will do, we will not flatten it, we will not destroy the arrangement. Simply, this is my image matrix. I will take a 2D array. So 2D array, say 1 is 1, 1 is 0.3. Then I will do one simple mathematical operation, which is called sum of product. Sum of product means 86 into 1 plus 4 into 0.3. So that will give me 87.2. And it will move to 4 and 8. Then I will do the same operation. Then 8, I will do the same operation. So in this way, I will try to sum of product by moving this particular 2 into 1 matrix. So this way, you can intensify the value with the weight, but you are trying to keep the 2D matrix as it is. But you are doing one operation, which is called the sum of product operation. This shift of this particular kernel, 1 into 2 kernel or window, is called stride. You are striding 1 pixel each time, and you are trying to find out the sum of product operation. And that sum of product, ultimately, once you do, observe one thing. Here there are how many numbers of column? 4 column. But if you do sum of product, the column number is 3. So somehow the number of column is getting lesser. Once the number of column is getting lesser, that means there is something problematic. Hello. Am I audible?
Yes, sir. You are audible.
Okay, so I got disconnected. Is this fine now? Okay.
Till,
Okay.
sir,
Okay. So
please
what I am
continue.
doing
Sir,
until
it is
now,
not
I think
yes.
is it visible now?
Yes, sir. Now visible.
Okay. Okay. So what I was saying that if we try to see, there is a say sum of product operation we are doing. So there are number of, say, column was 1, 2, 3, 4. But ultimately, once you multiply with an weight, you will see sum of product operation will give 3 columns. So there is a reduction. And another interesting thing to observe, if the weight is higher in left side, that is 1, and lesser in right side, that means 0.3, the output matrix, this particular side, left side is higher, right side is lesser. So there is an imbalance. So for that, what we need to do, we will simply patch 0 in both sides. Now, if you patch 0 in input matrix both sides, and if you do the same operation, you will see ultimately how many numbers of column. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So here 1, 2, 3, 4, 5, 6, 7. So this is called zero padding. We are trying to pad 0 in both sides, and then we are trying to do the sum of product operation. And after that, we will see that the number of column is getting same. There is no dimension reduction. So exactly input matrix and the output matrix dimension is same, but we need to patch 0. This is called zero padding. In this way, we can retain the input image dimension. But the one problem that the one side the value is increased, one side the value is decreased, that is not resolved. So for that, what we need to do, we have to multiply with a 2 cross 2 matrix, and you do the same operation sum of product, give a stride, but one side it is 1, this side is 1.5, here it is 0.3, and this side is 2. So that can balance these, and this particular output matrix is equally balanced. All the elements are almost similarly intensified. This 2 cross 2 matrix is basically called a kernel. And this kernel, you are doing a mathematical operation which is called sum of product. And that sum of product operation is nothing but convolution operation. So you are convoluting this particular matrix with this weight matrix and giving stride, and each and every stride, it will amplify the value. It will try to emphasize that value which I am searching for, and it is getting more prominent. So in this way, we can actually give input image into the neural network, and we can find out an individual pixel, or we can process an individual pixel. So this simple mathematical operation of zero padding and striding and multiplication of 2D array, say 2 cross 2 matrix, and giving a simple mathematical operation sum of product, ultimately gives the main flavor of convolution neural network. Now think from image point of view. If you have a 1-0 image binary pattern, this is your stride matrix. And what you are doing, you are striding it. You are not doing any segmentation. You are not doing any feature extraction. Just simply you are 1-0 matrix, you are striding it. For each stride, there is a patch generation. For all stride, it will give different patches. And all these patches are trainable patches. You don't need to go for region-based segmentation.
Sir, voice is breaking.
Is the screen visible now?
Yes, sir. Screen is visible. Now you are audible, sir.
Okay. Okay. So simply I am changing the filter. Maybe this filter is actually responsible to capture the horizontal information. Then if you change the filter from filter 1 to filter 2 and repeat the same process, like say you repeat the convolution operation, it creates a second level of features. So in this way, you can create multiple features or pool of feature only by changing the kernel and repeating the same operation, matrix operation. So this is another set of feature or feature map. So you have 6x6 matrix. This is your field. This is your 3 value. So who are contributing? First pixel, second, third one, not fourth, fifth, sixth. Then 7th, 8th, 9th is contributing. 10th, 11th, 12th is, then 13, 14, 15 is contributing. So it looks like 3, 1, 2, 3, then 7, 8, 9, and 13, 14, 15. So all the input image are not contributing for 3. They are not activated. Only a selected value are activated. And that is the basic essence of CNN, which is called shared weight, not fully connected neural network. If you tried it, if you do the same operation, filter 1, it will give you -1. For representing pixel 2, 3, 4, pixel 2, 3, 4, 8, 9, 10, and 14, 15, 16. So this is called the shared weight. So number of parameter getting drastically reduced. So last day I discussed about that how many numbers of intermediate layer required if you try to classify 1,000 classes. So you can imagine 60,000 different intermediate layers. So 6.5 million of different nodes are input nodes. So you can drastically reduce the number of parameters by minute because here the weight is getting shared. All the input pixel values are connected as an input network. So shared weight is the most important. You have different patches. You put all those patches. You pass through some model, say 1D vector, and you pass through neural network, and then there are different output. You put all together into a matrix. That matrix, from there you find out the max. It passes to the neural network. Ultimately, it will give you some output. It's a filter one. In this way, you can find out the for the one. So there can be max pool, there can be average pool. It depends upon which type of network framework you are using. But generally, we use the max pooling. So it's a generic framework of convolution neural network where the input layer and the convoluted layer are the pooling layer, and lastly your connected layer. So always remember one thing, that finally you have to convert the image into an 1D array. So it need to be passed as an 1D array either in the front or at the last layer. So last layer always should be a 1D layer, and it always should pass to a fully connected layer. So then ultimately you find out one, say, any kind of result. So if it is a softmax, you will get the probability, otherwise you will get the value. So in this way, there can be multiple level of convolution layer. So it depends upon what type of framework you are using. So this is one generic version of CNN, where you can see if suppose you consider X3, X3 is not connecting with all those association rule. So only they are connected with this one, and this one, not the fourth one. So it's a shared weight. It's not fully connected or dense neural network. So there is net exhibition function, there is activation function pass through. It might be ReLU or sigma or etc. Then ultimately after weight tuning, it passes through a fully connected neural network, and finally it gives a 1-0 value. So in this way, the glaucoma also you can deploy the same thing, and you can ultimately find out the disease having the eye having glaucoma or non-glaucoma. And then this is the glaucoma classification. This is the different pooling layers. And finally, as I said, you will get the, by some softmax layer, it will tell you the probability that you have glaucoma or not glaucoma. So lots of work has been carried out in this area where CNN people try to deploy in different ways. They try to deploy. And the now question is shallow learning or deep learning. So we should not always focus on that. Sometimes if you try to fuse these two, shallow machine learning and deep learning, it gives much more prominent result. Suppose in one of our study in breast cancer, we tried to deploy the CNN and as well as the support vector machine. And not only the handpick feature also we try to train. And in a particular data set, which is called RIM1 data set, we obtained some accuracy, which is very promising, where we try to fuse this kind of both data set, both vectors. This is CNN and as well as support vector machine. So 2-3 more slides left. One is the very advanced technique is called the, am I still audible? Someone is writing is not audible. Hello.
Audible.
Hello. Okay.
Hello.
Okay. Yes. Fine. Thank you.
Yes.
So the very advanced technique, which is called UNet. And UNet, what we need to do, we have to go for, looks like an U-shaped convolution neural network. But each and every, say, upsampling or downsampling, you need a benchmark. So this collection of benchmark is difficult. If you're able to somehow benchmark, up almost 100% accuracy. And in in glaucoma study, a very high accuracy actually obtained by people through UNet. So you can explore UNet also. UNet all, consuming, but it is very promising one. So in many kinds of CAD system, people are deploying UNet. This is a very new area. 2-3 years people are working in this area. Mainly from 2018-19 onwards. So lastly, there are lots of smartphone devices are coming out. We need lots of efficient, accurate, less time consuming devices, low cost CAD system. There are lots of different challenges like imbalanced data, the patient data, non-patient data, they are not equal. The nature of data, from where we are collecting the data, the quality of the data, the action process, the benchmarking of the data, and human biasness, these all comes into the picture. It is reported that 8,000 commercial CAD systems are running in states, but in India, the number is very less. So we have to come up with a new CAD system. And every day there are new types of diseases that are coming. Actually, COVID tells us the same story. So that's why designing CAD system is always important. It not only for the conventional diseases, but also for the diseases which are, which are actually we are facing, or maybe in future might be such type of scenario will occur. So you have to come up with some prediction models also. So there are lots of scope to work in this area, and huge work has been already carried out for breast cancer screening using of CNN CAD system. Say macro calcification detection, benign or malignancy for CAD system. There can be CAD system for the diabetic patient, which is one of our major research area where we try to deploy CNN for CAD system of diabetic patient, the way people used to work, and we used to collect the plantar image. So this is from our lab, that is a food scanner, where we find out from these sensors, there are total 8 sensors. From the, we used to capture the time series, and we used to analyze the time series. Based on that, we can find out the patient having diabetes or not. So this is from the lab in China. Lastly, yeah, this is our group. It's a grad student. This still in this area we are working, designing the shoes for the diabetic patient. And you can also improve the quality of the image. That is another area where the pattern-weighted image, how can you increase the quality? So I have a couple of works on this area, so you can explore from Scholar if you are interested. How can you capture the noise level and how can you improve the noise level, etc. Ophthalmo images also, like any ophthalmo diseases, to find out the macula, optical cup to disc, and the blood vessel, extraction of the vessel tree from vessel tree, as it is a biometric one. So for any ophthalmo diseases, it is always important to capture the vessel information. And as I already shown the optical cup and the disc, how to find out by CAD system. This is Q, how to quantify that calcium. As I said, you need to put a probe and you need to put inside the artery. So it's a intravascular ultrasound image where the calcification is there. So you have to find out how much calcium is deposited inside the artery and what is the problem for blood circulation from coronary or carotid to your brain, or what is the chances of stroke, cerebral attack, that you can measure by looking at the calcium, how much calcium it is deposited inside your artery. It's a non-geometric shape. That's why no geometric equation will fit in for this. So computation of this is very difficult. And we tried to find out the, how much, that means the volume of the calcium. It's not from the image itself. So it's always difficult to find out the volume from an image. You can get the area, but volume computation is always challenging one. So last but not the least, that it's always good to get good accuracy, but always be cautious about false positive. Patient don't have disease. If they are tested as positive, that is something problematic. So always we have to look into the specificity and the sensitivity. So always have to, the CAD system needs to be such a way that it needs to be designed that it is having the ability to test correctly, identify those patients without having disease. So if you don't have disease, the CAD should tell you that you don't have disease. It should not tell you you have disease. Otherwise, it will be horrible, terrible. So that's why false positive is an important factor. So you have to look into the sensitivity, specificity, PPV, NPV, etc. apart from the accuracy. So higher FPs, that means false positive, indicates the lower the specificity is. That actually reduces the acceptance of the CAD system, the overall performance or the acceptability of the CAD system. As I already discussed, the main challenges: imbalanced data, disease and non-disease data, nature of the data, from where you are collecting the data. It should be generic. You have to collect all around the globe. The quality of the data, benchmark data, and human biasness also there. Conclusion: CAD system actually now in deep CAD, there is a huge growth prospect, but still it's not that we are actually trying to discard this fraternity doctors. Rather, we always try to help the doctor to come up with the faster decision. AI actually beats the human doctors in few cases, few trials, but this is far away from the reality. AI can't beat human error, human expertise, human experiences, and it will take time over the period, maybe, but not now. We are far away from that. Thank you very much. So if you have any question, please feel free to ask. I will try to short the next session, as this session is almost now 1 hour 45 minutes running. So 40 minutes. So if you have any question, please feel free to ask. So the only thing our in chat box is not audible, sir. No audible, no audio, voice breaking. Okay, so I think no question.
Any question from participants side? Please write in chat box. I think no questions, sir. Yes, sir. One question.
Histopathological data, no? Okay, okay. Then another.
Sir.
Yes, yes, madam, please.
Good morning, sir. Nilanjan, sir. Myself, Renuka.
Yeah, ma'am, please tell me.
Sir, I have a doubt. I'm using single CPU, sir. What if I want to develop a CNN, do I have any cloud environment where I can get
Ma'am,
GPU
actually
processors?
your voice is not clear. Can you slowly please tell me?
Yes, sir. Is it audible, sir, now? Hello? Sir, am I audible now? Hello?
Please continue, please.
Yeah. Sir, actually, I want to develop a CNN, but I don't have GPU processors. I have a single CPU processor with 8 GB RAM. So, will I be able to connect with some processors, GPU processors in cloud, sir? Will I get such environment where I can compute
Actually,
remotely?
this problem I never faced because we have in university, but so if you to guide on it, they will write me a mail. I can connect it with the forum.
Okay.
That I can do. Again, I am repeating one thing that if you are doing it MATLAB, I mean, there are multi-process options are there, multi-processing. I think parallelly it can process 4 to 5 processes.
Sir, your
So
voice is
now
breaking,
MATLAB
sir.
21.
I'm unable to hear you. Sir, your voice is breaking.
Hello.
Hello?
Am I,
Not it, sir. Hello? Hello?
now am I audible?
Yeah, yes, sir. Now you're audible, sir. Please, sir. Yes, sir.
Hello.
You're audible, sir.
Okay. What I'm saying is the MATLAB, the latest version, the 21, you go through, you will see there is a parallel processing option.
Yes, sir.
Toolbox available which is related to CNN. Very latest one. So you can use that one. So
Okay.
if you are working on using G, then I try to connect with cities nearby who have that infrastructure. Otherwise, in our lab also we have problem. So if you are really interested, you can write on it for lab that I can connect with those fellows that I can do. And last
Yes,
thing
sir.
is there is an NVIDIA small kind of GPU to apply for a small grant from IE Institute of Engineers or somewhere else.
Yes,
They
sir.
sometimes I mean short kind of project. If you're able to come up with, you can go for an NVIDIA small setup. That is not too much costly. It's around 1.8 lakhs to 2 lakhs rupees. So that initial framework you can come up with. So a very short kind of project like CSI sometimes used to provide student funds, or IE also provides students funds. So if you're able to get such kind of thing, that will be a good option. But MATLAB, the latest version is something. Try. And regarding, there is another question, histopathology. Madam, histopathological images, they have their different kinds of nature. Means there is a group in Delhi who are actually working on histopathology in India. So histopathological data, I have a couple of books, 2, 3 books. Their CNN, I mean, apart from CNN, what I suggest you to go for fusion, because the main advantage of fusion is histopathological data. Actually, there is a color feature, which is one of the strongest feature which plays a significant role. So if you somehow the texture and color feature, if you use CNN framework or any kind of any other DL framework, I think that multimodal fusion will give you much more better result rather than only deep learning framework. Actually, today lecture I was trying to tell something like that. There should be some sort of shadow machine learning will be shadowed or will be covered in deep learning framework. So try to fuse it with pathological data. It will work fine. Not only CNN, fuse with traditional framework. Am I? Am I audible? Okay. So any more query?
Mr. Balaji Prabhu, you have a query? I have unmuted you. Please ask question.
Good morning, sir. Am I audible?
Yes, please.
Sir, yes, you were telling that yes, some of the deep learning architecture are powerful, or they are proved to better useful in some of the the application. And you told that Unity is one among them. Yes, I mean whenever using the image kind of data, or these kinds of huge data, big data, yes, of course we need to use deep learning architecture to get a better results, or to implement or to get the solutions. But whenever we are doing this as a part of our research, so what the panel members will say that, so yes, when deep learning is doing most of the thing, or all of the thing, maybe the feature extraction, everything is the deep learning is doing. So what is your work?
Good, good. So, sir, actually, you attended my very first session.
Yes, sir.
In
was
that
there.
session, I tried to give you the answer by explainable AI. Because now, if you are saying me that got 99% accuracy, why
Yeah.
should I believe you? What is the black box? Do you know inside that black box what is happening? Do you know which feature is particularly contributing for this deep learning model? So all these answers we try to explore, and that is only can be done by LIME kind of framework, LIME. That is the
Okay.
explainable AI. So I suggest you just I can share one link. 1 minute, please. In IEEE, just a minute. This is see it's not always blindly it's good to deploy deep learning. Rather, this particular article you try to go through one time. This is on Alzheimer, and this last week it published. So this study we try to first time actually from our group we try to come up with explainable AI. So it's not blindly CNN we deploy. Rather, we try to analyze what is the implications, how it is working, what is the main things are actually impacting the overall performance. So all these things are there in this short 8-page paper. It's a transaction paper. So first go through this. Again, I am telling one thing, that don't chase deep learning. Deep learning is nothing as such new. So without understanding the philosophy, it is not good to deploy deep learning. See, sir, today CNN, the way I started talking about it is simple a mathematical operation. It's a matrix operation, sum of product operation. So we need to think in that way, that it's blindly, simply you use auto encoder or say RNN or this. Rather, you think in this way, good result. That way, why it is giving me better result than the shallow machine learning? Which particular thing actually is the performance of CNN? So that need to be identified and properly. You have to justify it. So that is the result answer you will get from explainable AI. This study is basically that particular thing which is called a LIME, LIME, local interpretable model. So it actually interprets locally that model, explains the model. Okay.
Okay, sir. Thank you.
Thank you. So, Dr. Ram,
Yes,
so,
sir. Thank you, sir.
Give a break. Let's give
Yes,
a
sir.
break. I'm talking
Yes,
for
sir.
almost 2 hours. So we
Yes, sir.
start from 2:50. 2:50 is fine.
250, sir.
No, not 2, 12.
12:15, sir. Okay.
As you say.
12:15, sir.
Okay.
Yeah, half an hour. Half an
12:50.
hour break.
Okay.
Okay, sir. Thank you, sir. We will meet again at 12:15 p.m. Thank you, sir. Thank you all the participants. Have a lunch break, and we will meet again at 12:15 p.m. Thank you.